So as Michał said, today I'll speak about edit distance, and specifically I was asked to cover dynamic algorithms for edit distance. So in the first part, it will be more like in general introduction, and then in the second part I will cover some of the more recent results. And please interrupt me with questions whenever you have any, especially like during this first part. I want to make sure that everyone understands pretty much everything that I'm covering. Let me start with a very basic. So edit distance is one of the perhaps two most fundamental measures of sequence similarity or rather dissimilarity. So for two strings, you want to transform one into the other using character edits, which would be character insertions, deletions, and substitutions. So here, for example, to transform this x into y, you can delete the b, you can substitute the b for a, and you can insert a b at the very end. So here we have three edits, and you can also convince yourself that there is no way of transforming x into y using two or fewer edits. And this measure is very useful for various applications, like in bioinformatics, or for example, if you want to correct spelling errors or OCR errors, all kinds of errors like that. And the problem of computing edit distance is a very old one. It's been introduced already in the late 60s and early 70s. And several communities independently discovered a very simple quadratic time dynamic programming algorithm. So these were both some natural language community, some bioinformatics community, and more of theorists. So for strings of length up to n, we know how to compute the edit distance in n squared time. But if edit distance is smaller than that, we can do faster. In late 80s, Landau and Vishkin devised an algorithm with running time n plus k squared, where k is the value of the edit distance, how many edits you need. And by now, we know that these running times are essentially optimal. There hasn't been any significant improvements, only by some polylogarithmic factors. And more like 10 years ago, one of the first big achievements of finite complexity was to show that any sub-quadratic algorithm for edit distance, and a truly sub-quadratic one like n to the 1.99, would violate a strong exponential time hypothesis and even orthogonal vectors hypothesis, which some find more believable than SETH. And under the same assumption, this quadratic dependency on k is also optimal. So for any reasonable value k, the running time n plus k squared cannot be significantly improved. So computing edit distance itself is a fairly well understood problem. And today I want to talk about the dynamic version of this problem, where the strings change over time. And after every change, we still need to report the edit distance between those two strings. And the changes we will support are also character edits themselves. So we can start with the same instance we had at the beginning. Here the edit distance is 3. And now the user can make some change to one of the strings. For example, you may insert this b here. And now the y string has changed, so we need to update the edit distance. And in this case, this was kind of a favorable update, so the edit distance decreased from 3 to 2. We can also make substitutions, like here. And this substitution didn't change the distance, although it did change the optimal alignment. And here we have another update, a deletion in y, and the edit distance went back to 3. So the task is to support this kind of edits, and after each update, we want to recompute the edit distance. And ideally, we don't want to recompute it from scratch. We want to somehow use some information of the from the previous time step to quickly update the edit distance. And kind of a folklore solution, which comes by combining Landau-Vishkin algorithm with a very early dynamic strings data structure, shows that you can achieve update time quadratic in the distance. And here in this O tilde notation, I'm hiding some polylogarithmic factors in terms of n, the length of the strings. So this was kind of known already in the 90s, although I'm not aware of any. Yes?
So just a quick question. K is the current edit distance, or is it some upper bound that's...
It is essentially the current edit distance. The current and the previous one can only differ by 1.
Yeah.
So basically, it doesn't matter if you want to consider the one before the update or the one after the update. You can also have a version where you have some kind of bound on the distance, and the update time would be this bound squared, and whenever the distance itself is larger than the bound, the algorithm would just tell you it's above the threshold, so it wouldn't give you the distance itself. So I'm not aware of any paper like from the 90s explicitly stating this result, but it's a kind of followed by easy combination. I will show this algorithm in a few minutes. Then there was a fairly long line of work that worked for updates only happening at the endpoints of the two strings. Initially, these were like incremental algorithms or online algorithms which just allowed appending characters to the end. But then, after a series of works, Vishkin showed that you can actually append and prepend characters and append and remove characters from either endpoint of either string. And each of these update time is linear. And this linear update time is optimal because you could start from empty strings and create a worst case instance simply using n insertions at the endpoints of the strings. And more recently, with Panos, Regis-Arampopoulos, and Shai Moses, we showed that new linear update time is also possible for arbitrary updates. So now you can have updates anywhere in the string, and here the update time is n log squared n to be more precise. And the more recent result that I published on I put on arXiv like last month with Yegor Gorbachev, a student at MPI, we showed that actually the update time can be decreased from linear in n to linear in the distance k. And today I will first cover the standard static algorithms, mostly to set up some notation and terminology. Then I will explain this folklore k-squared update time algorithm. And still in the first part of the tutorial, the new linear update time in n. And then in the second part, I will cover the new result with update time k. And also, if time allows, I will say something about dynamically maintaining not the exact, but approximate edit distance.
So do you have any law found that the order of k update time is
yes, tight? It is tight, and that's because, again, you can start with a string of all zeros, which is not very interesting, and then you can add a worst case instance of size k. And this worst case instance is inserted in k steps, and this quadratic time in k is necessary based on orthogonal vectors conjecture. So yes, also we cannot have, you can only hope for bring the log factors or sub-polynomial factors in this order of k dependency. Any more questions? OK, so let me start with the static algorithms. And the way I want to view the edit distance problem is by computing a shortest path in the Centron graph. So here we have the two strings. The string x is the horizontal one. The string y will be the vertical one. And we have a grid spanned by the characters of this string. So for every pair of characters, we have a grid cell. And here the horizontal edges will correspond to deleting characters from x, vertical edges to inserting character in y, while diagonal edges will correspond to either making a substitution if the character are different, like here, the red diagonal edges. And for the green diagonal edges, we will have matching characters. So for every red edge in this graph, you need to pay 1. For every green edge is free. This costs 0. And now the edit distance can be interpreted as the shortest path from the top left, the distance between the top left corner in this graph to the bottom right corner. And this shortest path can be also interpreted as an alignment between the two strings. So here we have this blue path, and here we have an alignment. So the path matches the first character, then deletes the b, matches 4 more characters, then makes a substitution, 3 matching characters, and finally inserts a character at the end of y. And this is exactly the alignment I have also drawn on the right-hand side. And now when we have such a graph, it's an acyclic, directed acyclic graph of size n squared. So the classic DP is simply compute the distances. OK, one more thing, that we have multiple shortest paths, so they also correspond to multiple alignments. But the classic DP algorithm simply computes the distances from the source vertex to every other vertex in this graph. And that's fairly standard because it's a cyclic graph of size n squared. And that's how we can compute the distance. Now, if you know that the distance is small, we don't need to compute the distance to all the vertices. So instead of processing the vertices, let's say in row by row, as would standard DPU do, we can process them based on the distances. So we start with vertices of distance 0. Then we discover all the vertices at distance 1, at distance 2, and finally at distance 3 in this case. And since the target vertex is already at distance 3, we don't need to discover any more vertices. And this is also a fairly standard version of BFS when you can insert, when instead of the normal queue, you have a double-ended queue. So whenever you have an edge of cost 0, you insert it at one end of the queue. Whenever you have an edge of cost 1, you insert it at the other end of the queue. And this way, you can process the vertices ordered by distance whenever the distances are 0 or 1 in your graph. And here, whenever the distance is bounded by k, we know that the vertices we explore are either on the main diagonal or k diagonals away in each direction. And that's because whenever you change the diagonal, you need to use a horizontal or a vertical edge, and this costs at least 1, or exactly 1, actually. So the number of vertices you explore in this way would be n times k. And this is like a classic n times k version of the DP algorithm. Alternatively, you could just forget about the vertices outside this band and compute the distances in the remaining graph. For the distances which are, for the distance to the bottom right corner, it wouldn't make a difference. Some other distances may change if you view this in this alternative way. Okay, this is n times k, but actually this approach can be implemented in n plus k squared time. And for this, let's just analyze it a little bit more carefully. So we know that the source vertex has distance 0. So what kind of other vertices may have distance 0? Well, we need to start with some vertex which already at distance 0, which is this one, and then we can follow free edges. And the free edges are only on the diagonal. So essentially, we ask how far we can go along this diagonal until we encounter an edge of cost 1. And this corresponds to how many matching characters you have when you start at the beginning of your string. So the longest one prefix of the two strings. In this case, the first characters match, the second characters do not. So we have one extra vertex of cost 0. And now, let's understand how to get a vertex at distance 1 from the source. Obviously, if you start from a vertex of distance 0 and you follow any of the red edges, you will get a vertex of distance 1. And then you can have more vertices at distance 1 by following the free edges. So for this, we look at all the diagonals. And in this case, there will be only 3 diagonals where we already have vertices of distance 1. And for each diagonal, we ask how far we can go without encountering any mismatch. So now it's again, we're asking how many characters match until we have a mismatch. But now we don't start at the very beginning of both strings, but at some other positions in the two strings. In this case, 4 characters match. The 5th one does not. And we can proceed this way for other diagonals. Here we have no matches. And here again, we have 4 matching characters. Now we have all the vertices at distance 1. And we can continue with the next distance 2. So first, we propagate to all the neighbors. And then we follow the diagonals. And an important property here is that at each diagonal, the distances are non-decreasing. And this can be proved by a simple induction. So whenever the distances, the set of distances, vertices at distance at most 1 was kind of a prefix of every diagonal. And then when we move to the neighbors, it remains the prefix of the neighboring diagonal. And that's true because all these red edges have the same cost 1. It wouldn't be true if you had some other weight. So if inserting and deleting different characters would have different costs. So now we have this vertices of distance 2. And again, we have 5 diagonals to cover. For each of them, we need to ask how far we can go until we encounter a mismatch. And then distance 3, 7 diagonals. Some of them already reach the end, so we don't need to do anything. And actually, with distance 3, we are done with the algorithm. And here, since we have this monotonicity property, we only need to record for each of these diagonals how far we can go with every distance. So we have k or 2k plus 1 diagonals that we need to consider. And for each diagonals, we have k plus 1 thresholds in the worst case. Like when does the diagonal jump from 0 to 1, from 1 to 2, from 2 to 3, and so on. And the Landau and Vishkin algorithm doesn't maintain these distances which I'm drawing. It just maintains for each diagonal how far you can go with every distance. And then you can do it for the distances. Then you propagate this to the neighbors, and then you extend with LCE with the queries of what's the longest common prefix starting at the given position. And the number of queries you are asking is quadratic in the distance k. 2k plus 1 diagonals, and for each diagonal at most k plus 1 queries. And these queries are technically what's known as longest common extension or LCE queries. So you have the two strings, and we are asking for two given starting positions how far you can go without encountering any mismatch. So what's the longest prefix of the suffixes starting at position x and y respectively. And kind of the technical contribution of this paper of Landau and Vishkin was that these queries can be answered in constant time after linear time preprocessing. If you know what the suffix tree is, then this is lowest common ancestors in the suffix tree of the two strings. And this immediately gives the algorithm running in time n plus k squared. So this n is the preprocessing time, and k squared is the number of LCE queries, each implemented in constant time. And to have a dynamic counterpart of this algorithm, it suffices to observe that LCE queries can be implemented in polylogarithmic time in the dynamic setting, with updates also supported in polylogarithmic time. And this is what Melchorn, Sundar, and Ulrich already did in the first half of 1990s. Originally, this polylogarithmic dependency was quite high. By now, we know that with randomized algorithm, we can get a single log n factor. With deterministic solutions, there is some polylog term on top of that. But today, I will not focus too much on the polylogarithmic terms. So the update time of the dynamic algorithm is just O tilde of k squared. So k log n if you allow randomization. Okay, any questions? So that's the first kind of folklore solution. And now let me move on to this new linear update time algorithm with Panagiotis Charampopoulos and Shai Moses. And first, let me focus on a slightly simplified version of the problem, where all the updates we support are actually substitutions. Note that we are still maintaining the edit distance. So the distance we want to compute still makes insertions and deletions, but the updates, how the strings change over time, are only substitutions. Then we will generalize this solution to support edits. So what the effect of a single substitution is, so if we change a character in x, then the only thing that changes is the weights of the diagonal edges in the column corresponding to the substituted characters. Similarly, if we have a substitution in y, what changes is the diagonal edges on a single row of this matrix. And now, as we make more and more substitutions, you would like to understand what information we need about the parts that have not changed. This would give us kind of an insight what kind of information we should store and maintain as the strings change over time. So let's focus on this particular region, which hasn't been affected by any of the updates. And how can the shortest path, the optimal alignment, interact with this region? It can be disjoint with it, of course, but other than that, it can enter it somewhere on the top left boundary. And then it can leave anywhere in the bottom right boundary. And that indicates that the information that would be very useful would be all the distances from the top left boundary to the bottom right boundary. And that's what is known as the dist table or the distance matrix. So we have this alignment graph. Now I'm kind of zooming into the region which didn't change philosophically, but I'm just defining it for any two strings. And here I'm no longer interested only in the distance from the top left corner to the bottom right corner, but in any distance from what I'll call an input vertex, which is a vertex on the left boundary or the top boundary to output vertex, which will be on the bottom side or on the right boundary. And I'm enumerating these vertices starting from the bottom left corner towards the top right corner. So here is the input from 0th input all the way to the last input, and outputs from 0th one all the way to the last one. And now I'm interested in a matrix which stores all the distances between the input and output vertices. So for example, the entry in the row 10 and column 10 would be the distance between the 10th input and the 10th output. In this case, this is the distance of the two strings, and this value is 3, as we have seen earlier. This term, on the other hand, in row 8 and column 13, the distance from input 8 to output 13, in this case, it's 5. We have these matches and 5 horizontal edits. Now this matrix is slightly annoying because some of its entries are actual values, integers, but others are infinities. And that's because we have a directed graph. So for example, we cannot get from input number 4 to output number 15 because the edges are all pointing downward, and this would require moving upwards. But it turns out that we can forget about the directions of edges. So we make an undirected graph with the same costs. And all the infinite entries in the matrix will become finite, while all the finite entries will not change. So why it cannot change? Why they cannot change? Well, now the shortest paths can do very crazy things like this. But it turns out that whenever a shortest path is like that, you can always shortcut it. And that's because whenever you have a path that is not monotone in both coordinates, then it will visit some row or some column twice while leaving this row or column in between. And now we can simply straighten the path by just following the edges on the row or on the column. And here we are using the fact that these endpoints of this shortcut are on different diagonals, and we need to pay at the shortest path, whatever it does, it needs to pay at least 1 to change the diagonal. And here we are just paying 1 to change the diagonal. So this path is always always cheaper or equally expensive as the path that does some crazy thing in the alignment graph. So for every pair of vertices, there exists a shortest path which is monotone in both coordinates. That's true both for actual paths we care about, when the starting vertex is above and to the left of the end vertex, but it's also true for the path in the opposite direction. And now we have a graph. It's actually an undirected planar graph. So it satisfies what's known as the Monge property. So whenever we have 4 entries in this matrix that form a rectangle, we can look at the 2 entries on 2 opposite corners. This 3 and 5. This would be the shortest paths. And these shortest paths necessarily intersect. That's because if you want to go from input 10 to output 10 and from input 8 to output 13, you must intersect somewhere. You will need have some non-planarity, some bridge to jump over this path. And now if you want to, instead of computing distances from 10 to 10 and 8 to 13, you want to compute the opposite pair of distances. So from 10 to 13 and from 8 to 10. You could also use the original path, simply changing how they are connected in this crossing point. And this would be some paths between those 2 pairs of vertices. Perhaps they are not optimal. It's possible to shortcut them and then get cheaper paths. So in this case, these 2 are now not the shortest paths, but these 2 are the shortest paths. And in terms of the values in the matrix, this means that those 2 blue entries, when you sum them up, are always more expensive than those 2 violet entries. So here we have 3 plus 5. It's strictly more than 4 plus 3. And matrices satisfying this property are known as Monge matrices. And actually, when you have this excess, so here we have an excess of 1 unit, because 8 is by 1. 8 minus 7 is 1. We can trace this excess to a particular 2 by 2 rectangle, 2 by 2 square in this matrix. So when we have an excess of this whole rectangle, it behaves linearly, so it can be decomposed into excesses of all the 2 by 2 squares within this rectangle. And here, for almost all of them, there is no excess. But for this one square here, we have an excess, because 4 plus 4 is 8, and 4 plus 5 is 9. So in this matrix, whenever I have such a tiny square with some excess, I can mark this square. And here I have marked by just a black circle all the squares with excess 1. And the black circle with a ring around it is whenever the excess is 2. And it turns out that you can never have more excess than that. And that's because the values in the leftmost row and the rightmost row are simply integers starting from 0 to the length of the two strings, x plus y. And in the other opposite column, they are just in the inverse order. And for every such very flat rectangle, here we have two integers, x and x plus 1. And here we have integers y and y minus 1. And here the excess is 2 units. So for every row, we have in total an excess of 2 units. They can be in a single location, or they can be split into two different locations. Similarly, for every column, you have an excess of 2 units, and they be similarly separated or in the same location. And that means that the number of these weighted points, either with weight 1 or 2, is always bounded by twice the total length of the input strings. And in particular, this can be used as a linear space representation of our distance matrix. So whenever you want to compute some value, for example, you want to recover this value in the violet cell, you can look at the other 3 entries at the endpoints of this rectangle, at the corners of this rectangle. And we know that this is always 0. For the row number I, this is I. For the column number j, this is j. And then we need to count how many points, or what's the total weight of the points inside the rectangle. Here, if you count them, it turns out to be 14. And this 4 can be viewed as 10 plus 8 minus 14. So this gives a representation of the distance matrix in linear space in terms of the lengths of the two strings. Putting this more formally, so we have this notion of Monge matrices. And here this M square is sometimes called the density matrix. And it simply records the excess in each 2 by 2 square. So the total value of the 2 corners minus the total value of the other 2 corners. And for every matrix, even if it's not Monge, we can retrieve any entry by looking at the leftmost entry in this row, the topmost entry in the column, subtracting the top left corner of the matrix, and then we sum up the excess values to the left and above the value the cell you want to compute. And for matrices we encounter as distance matrices, this density matrix is quite sparse, and its non-zero entries are called core in the literature. So whenever we have a matrix whose core is only of size c, then you can encode the matrix in space which is linear in the dimensions, plus c log c, where c is the size of the core. And now every entry can be computed in logarithmic time in the size of the core. So these kind of queries that are working behind the scenes are known as orthogonal range counting queries, or orthogonal range semi-group queries, because we have weights. So we simply need to count what's the total value of these excess points in some top left part of the matrix. In our case, the matrix is Monge, and also its core is always linear in the lengths of the two strings. So that's why this representation takes new linear space in the lengths of the strings. OK. So actually, this kind of insight was already there in late 90s. Donette Schmidt also proved that the distance matrix can always be computed in quadratic time. So in this time n squared, you not only can compute the single distance from the top left corner to the bottom right corner, but all the distances between the input boundary and the output boundary. Today I will not show this algorithm. I will show something that implies an extra log factor on top of this runtime. So the way we will construct distance matrices, which will be useful in the dynamic setting, is by stitching them together from smaller matrices. So we will start with distance matrices for the very simple instances where the strings are of length 1. In this case, we have just two possibilities. Either the two characters are the same or are different. And we have two kind of basic building blocks in terms of distance matrices. And then, whenever we have two alignment graphs for the same string, in this case in the vertical dimension, you would like to be able to glue them together using these thicker red edges. And the way we will do it is we'll start with the distance matrices of these two alignment graphs independently. Of course, represented in this cost-plus representation. And then we will slightly modify the graph by adding these extra vertices here and these extra vertices here. So now, instead of just gluing this column, I want to glue the entire polyline consisting of 3 segments. And why is this useful? Well, whenever you consider the graph glued together, this will form a separator between the top left boundary and the bottom right boundary. Whenever you have a kind of reasonably looking distance from the starting in the left part and ending in the right part, it of course needs to cross somewhere the boundary. We don't know where it does, but the distance matrix gives us all the distances from the input to this separator. And then the other distance matrix has all the distances from the separator to the output vertices. So we have these two vectors, a row here and a column here. And the distance is just the mean plus product of these two vectors. So that's why the operation we want to make on these extended matrices is just the mean plus product of the matrices. And here this extension is very simple. So we just add core entries at the diagonal. And they are like double core entries with value 2. That's because any path to or from these extra vertices necessarily goes through one of these corners. And then you just add the number of vertices on the extension. And this mean plus property also holds in in less natural cases. Like if you want to compute a path which is already in the right graph, you can view it as starting in these extra vertices and just going to the other part already at the beginning. Or also this works for paths going in the opposite direction. And that's true because these paths will never cross the separator multiple times. Whenever we have a path going backwards, it needs to change many diagonals. So any Manhattan-like path is of the same cost, in particular the one that follows the diagonal. So now we can compute actually the mean plus product rather than some completion where you need to consider crossing the separator multiple times. All right, so we have, and here is where we will use the Monge property of the matrices. So for general Monge matrix, for two general Monge matrices, it is known that their product in terms of the mean plus operators can be computed in n squared time. Normally it's n cubed for arbitrary matrices. For Monge matrices, n squared. But it turns out that if the matrices have small core, then this quadratic dependency on the dimension can be reduced to new linear dependency in the size of the core. And here the bound on the size of the core needs to be true both for the input matrices of the mean plus product and also for the product matrix. But in our case, all the matrices we are computing are distance matrices. And we already showed that their core is of size linear in the length of the strings. And this result was first proved by Vishkin in 2008 for a special case of so-called unit Monge matrices, where these points in the core are one in every row and one in every column. But then Luis Russo generalized it to arbitrary matrices with small core, paying some more log factors, which I'm anyway hiding in this O tilde notation. So what it means for our applications for edit distance is that whenever you want to compute the distance matrix for strings x and y, you can start with distance matrices for xl and y and xr for and y for some partition of x into xl and xr, and you can just combine them using this operation from the previous slide. So you extend the matrices and then compute the mean plus product. And similarly, you can decompose this box vertically. So you partition y into left and right part, and then you combine the distance matrices for xyl and xyr. And yes, this algorithm I will not cover in the presentation because it will take me like another 20, 30 minutes, but it's not very complicated. It's like a few pages in the original papers. But now let me go back to the dynamic algorithm for maintaining the edit distance. OK, so we have this alignment graph. And what we can definitely do is we can build a distance matrix for every single cell in this graph. And then we can keep combining these tiny cells into larger and larger boxes. So we will simply use dyadic intervals. So he will have boxes of size 1 by 1. And then every such box can be grouped together with 3 of its neighbors. And we will have a partition of this grid into boxes of size 2 by 2. For every box of size 2 by 2, we will need to combine these 4 smaller distance matrices. So let's say that first we do it horizontally. So these two get merged, these two get merged, and then the 2 by 1 matrices get merged into a 2 by 1 boxes get merged into a 2 by 2 box. And we can continue making boxes larger and larger until we compute the distance matrix of the entire alignment graph. And this matrix contains an entry representing the edit distance between x and y. In terms of the running time, so computing the distance matrices for these 1 by 1 boxes takes constant time per box, so n squared in total, because these are just objects of constant size, which we can hard code in the algorithm. While for every box of size 2 to the L by 2 to the L, we obtain it by combining 4 smaller boxes. And this combine operator takes linear time in the dimension of the box. So 2 to the L up to log factors. And the number of boxes of size 2 to the L by 2 to the L is n squared by 2 to the L, and everything squared. So for every level in this algorithm, we pay n squared over 2 to the L time in total. And throughout the levels, this is some geometric progression, so we get n squared again. So that's how the preprocessing polydynamic algorithm will work. And now we have all these distance matrices for boxes of various levels in the hierarchy. And now whenever a character is substituted, recall that we only needed to change the weights of diagonal edges in 1 column or 1 row of this alignment graph. Let's focus on the case when it's a 1 column. And now the only 1 by 1 boxes affected are those actually in this column. So for those, we will need to recompute everything. Then for every 2 by 2 boxes, also they form a single column in the larger scale. And so on, for every scale, we will need to update or recompute the distance matrices for boxes lying in a single column of this alignment graph, until we finally get, again, the distance matrix of the whole string. And from this, we can retrieve the edit distance between x and y. And now, for every 1 by 1 box, we pay constant time, so it's linear in total. While for every scale L, again, we just compute the distance matrix kind of from the 4 smaller pieces. We don't use the previous distance matrix for this scale. We just forget about it. But this is cheap enough. So we have n over 2L affected boxes of this scale. And for each of them, we pay 2 to the L up to the log factors I'm hiding. And overall, the runtime would be near linear. That's because we have near linear time at every step, and the number of steps is logarithmic, because these sizes of the boxes grow exponentially as we proceed to the subsequent level. Now this was very easy for substitutions only. To make sure that we also allow insertions and deletions as updates, we cannot just use boxes of the rigid size 2 to the L by 2 to the L. That's because such a rigid grid, like here, it would not. Many boxes will change when we add a single column or a single row. So that's why we will relax this condition. So at level L, instead of insisting that the boxes are of size 2 to the L by 2 to the L, we will allow their dimensions to be anywhere between 2 to the L minus 1 and 2 to the L plus 1. And with this, we can still make sure that every box of a given level L still can be decomposed into constantly many boxes on the previous level. This number is actually at most 49, because we have ratio 4 here. Within the single level, adding one more level, the ratio is 8. And since we have strict inequalities, it can be at most 7. And 7 squared is 49. OK, so now what happens when we, let's say, add a new character to X? In the alignment graph, we now have a new column. So we can compute these 1 by 1 boxes, 2 by 2 boxes, and so on. But sometimes, at some levels, we might have boxes which are too wide, because they were already at the maximum width, and now we have inserted one column, so the width would increase beyond the allowed range. And in this case, we will always be able to simply partition the box. Like here, we have a box of width 4 at level 1, which is too large. But we can always partition it into 2 boxes of the same level. And if you do some calculations regarding this threshold, this is always possible to make sure that this partition preserves the structure of the boxes at the previous level, so we don't partition the box at the level minus 1 somewhere in the middle. And also, none of these 2 pieces is too small. Basically, we partition as close to the midpoint as possible, because whenever the box is too wide, it will be of width exactly 2 to the L. And then we may need to fix this not only for one scale, but for multiple scales. But this is fairly independent between scales. Similarly, when we delete some character, let's say deleting character in Y, we remove the row in the alignment graph, and some boxes might become too short. And then we will be able to, like here, if the box is too short, this is a box at scale 2. It should be of length strictly more than 2 in this law of height 2. So we will merge it if it's neighbor. But now it can be too tall. So we may need to split it somewhere else, like here. And again, with this threshold, it's always possible to split so that the invariant is satisfied. And if you, like in the paper, originally we wrote this part kind of from the basics. But actually, this can be interpreted as maintaining what's known as weight balanced B trees for some constant B, like B equal 2 to be precise. So there's a paper by Arge and Witter which shows how to maintain B trees. And we can think of this hierarchy both in terms of horizontal hierarchy and vertical hierarchy as a B tree built on top of the 2 strings. And this grid is kind of the Cartesian product of the 2 B trees. And just like for substitutions, every update affects only one row on one, or actually 2 rows or 2 columns of entries at a given scale. No, it used to be 1 for substitutions. Now it's 2 because we have sometimes are splitting, and when we are splitting, we get 2 affected columns or rows at the given level. But nevertheless, the running time is exactly the same. These rebalancing operations are much cheaper than what we are doing with distance matrices. And that's the result we got in this 2020 paper. So we showed that the edit distance can be maintained dynamically with update time n log squared n. And the key tool for this, and the tools that I will need you to remember for the second part of the tutorial, is that we have this notion of distance matrices. They have quadratically many entries because they store all the distances from the boundary to boundary, but they have linear space representation. And this representation can be combined efficiently and can be also maintained efficiently. So the algorithm I have presented, the task it was designed for was just to maintain the distance from the top left to the bottom right corner. But this algorithm actually maintains the whole distance matrix. So we could only have queries asking for any what's called semi-local distance. So any distance from the top left boundary to the bottom right boundary. And I think this is a good point for a break, even though it's earlier than in the schedule, because the second part of the talk is slightly longer than the first one. So let me take a break here and take some questions for now, and then we will reconvene, I guess, in 30 minutes or so.
Thank you. Questions?
Yeah.
So it seems like your pre-processing time is something like order n squared.
Yes.
For these like hardness results, like clearly if I use the exponential space, I would be able to do better. Is there something where if I'm allowing myself like a larger polynomial with pre-processing time, I can improve the? Is there some sort of up there?
You cannot really do much because like you could start with kind of very boring strings, like all zeros or even empty strings, and pre-processing them wouldn't help you because after an update you can still get a worst case instance. Like you could, if the lifetime of your algorithm were very short, like you could only support, let's say, constant number of updates throughout the lifetime of the algorithm. You could kind of pre-process for every possibility of this constant many updates. But as long as the lifetime is like n updates, you cannot achieve anything for that. Yeah.
So this is kind of like maybe it will be clear like later, but. So now, like, what if you have like k updates? So you have like n squared time pre-processing, so you can like compute a lot of stuff, and then you have k updates. Could you hope that there will be something where actually the update time depends on the number of updates you make?
Like for small constant, yes, but I'm not aware of anything other than that.
Is it excluded by some conjecture?
I mean, you can, because you, no, I don't know. I wouldn't think about it.
Thanks. Questions?
A similar question to the other two. So you said you can improve the update time from n to k.
Yeah.
Can you improve the pre-processing time from n squared down to k squared?
Yes.
Okay.
I will discuss this after the break. Like it's n plus k squared or
Yeah.
to be precise.
Thank you.
Mm-hmm.
Oh, sorry.
Yeah. Maybe just a quick question. The size of the data structure is n squared, right? Order of n squared.
Up to log factors, definitely yes. I don't remember what are the log factors in the space complexity.
Is it possible to improve upon this?
We haven't tried, but like we haven't tried. That's a nice question.
I have questions on this chat.
Oh, how do I access them?
Yeah, you can click this.
I can say actually, can you hear me?
Yes, I can hear you. It's worst case.
Hi, that's Negev. I just want to ask, the balancing procedure, is it near linear for every update, even when you need to change the size, to cut the boxes, or is it just the amortize on average?
It's worst case linear per update. So at every level, you always perform just one kind of rebalancing step. So you always.
In this case, why perfect? Why can't you stay rigid and always make it precisely the right balance, or you need this range because it needs to be multiplied by 2.
I mean, because like you cannot be rigid, because if you have a rigid structure, then any operation at some point would affect the whole suffix afterwards. And now it's usually only affecting very local region of this boundary. So for every level, you may need to merge or. So for insertion, let's say you can make one merge per every level, but it's just one merge. And nothing like shifts afterwards. But that's like, in principle, it's the difference between classic B trees and these weight balance B trees by Arga and Viter. So they already kind of did the heavy lifting and showed that you can do everything in the worst case. In their case, like the worst case polylogarithmic time, because they don't have these distance matrices.
And that's because you need to cut it by 2 or combine 2 exactly the same time.
Yeah, so you need to like split it somewhere, and you need some slack to be able to make sure that before the split and after the split, they are still within the range of allowed sizes.
Okay, that makes sense. Thank you.
Thank you.
Other questions? Thank you.